Today we're going to take a look at what a solar system is. Now in today's lesson we're going to be focusing on our solar system, but it's important to understand that there are many solar systems out there in the universe. When I say many, we're talking billions upon billions upon billions. A solar system is basically a star and then any objects that are in orbit around that star, or we would consider them to be satellites of that star. A satellite is any object that orbits another one. So a solar system would be a star, and then any planets, meteors, anything like that, that would be in orbit around it. We're going to focus in on our own solar system, but again, realize that every star has its own solar system. So in our own Milky Way galaxy, there are about 200 billion stars. That means we have about 200 billion solar systems. And when we think of all the other galaxies out there in the universe, there's probably almost an infinite number of these things. Each one of them could have planets orbiting those stars. So when we look at our own solar system, first thing I want to point out, almost none of the diagrams we look at today are going to be in scale, because the distance between the planets would have to be so far apart to make them to scale that we wouldn't be able to fit them on a screen. So just realize that. They also typically show the planets all in alignment, and in reality, they're almost never perfectly in alignment like this, especially when we start thinking in terms of three-dimensional aspects of its orbit. But in our own solar system, and of course the sun is the most important part, and we're going to break this down so we can look at all the different parts of this. Sun is the most important part, and then we have our 8 planets: Mercury, Venus, Earth, and Mars. And these first four that are closest to the sun, are very similar to each other. We call those terrestrial planets, which we'll talk about later on. The little graphics you see under it are how many moons we have, and there are others that aren't labeled here, but Earth has 1 moon, Mars has 2. We'll talk about moons as well. Then we have an asteroid belt. They named a couple of them in here, and there's plenty more. This is a belt of rocky and metallic fragments that exist between Mars and Jupiter and orbit the sun, and we'll talk more about that. Then we get to Jupiter, Saturn, Uranus, and Neptune. These are the gas planets. We call them the Jovian planets, and they're much, much larger, and they don't have solid surfaces that we know of like the first 4 planets do. And these have many more moons, as you see listed here. They list the biggest and most impressive ones, and then they have others listed down there. We'll go through the moons of those as well. Then we get to something known as the Kuiper Belt, which is similar to the asteroid belt. It's just much farther out. Pluto is believed to be an object that is part of the Kuiper Belt now and no longer considered to be a planet. It's called a dwarf planet. Then we get to something called the Oort cloud. And the Oort cloud is this theorized cloud of icy bodies, which would basically be the nuclei for comets that we see occasionally passing through our solar system. We'll take a closer look at comets in a lesson next week. So we're going to kind of take this piece by piece, go through all the details of our solar system, and you'll have a good feel for it by the end of this lesson. If you want, having page 15 in your Earth Science reference tables open, there's a solar system data chart. You may want to have that open. We're going to refer to it from time to time throughout the lesson today. So since we're dealing with the solar system, and the word solar has to do with the sun, which is the star at the center, and since we're using our solar system, we're going to focus on our sun. But remember, each solar system has its own unique star. So Polaris has its own solar system, Proxima Centauri has its own solar system, and that's true of all the stars that are out there. But we're going to focus on our sun, which is the most important part in the center. When I say center, I say that loosely. We're going to explain that too. It's not perfectly at the center, but it's the object near the center of our solar system. Our sun is a medium-sized main sequence star. It's pretty much average in all respects. We estimate that it's about 5 billion years old, and it probably has about another 5 billion years or so to go before it runs out of hydrogen and starts to convert into a red giant star. So we've got about 5 billion years left here before we have any issues with that. And the sun is the most massive part of our solar system. 99% of the mass of our solar system is contained within the sun. And that's why all the objects revolve around the sun and not the other way around. So the planets, asteroids, meteoroids, comets, all things we'll talk about today, they're all what we call natural satellites of the sun. Satellites are any object that is orbiting another. So if we want to apply this to the Earth, what is the natural satellite of the Earth? Well, that would be the moon. That's the object that's orbiting around us. And of course, there are man-made satellites, which we put up into space, that orbit as well. Now, when we look at the sun, we don't necessarily get to appreciate the fact that it has its own structure as well. So when we think about the sun, in the reference tables, they tell us the surface temperature of the sun is about 6,000 Kelvin. But That's the surface temperature. As you get into the interior of the sun, it gets hotter and hotter and hotter, much like the Earth does. And by the time you get to the core of the sun, where that nuclear fusion process is really taking place, taking that hydrogen and fusing it into helium, you're talking about temperatures in the millions of degrees. If I remember the number correctly, it's about 24 million degrees at the center of the sun. So that's what they call the core. Then we have something called the radiative zone and then the convective zone. And that's really what you're kind of seeing the edges of when we're taking a look at this in pictures. And then on the surface, there's all sorts of kind of things that we're taking a look at. We have what's known as the chromosphere. We have these things that are called solar flares and prominence that come off the sun. It creates something called the solar wind, which is the stream of charged particles. The corona can almost be thought of almost like the atmosphere of the sun, even though it's not the right word to use. It's sort of the gases that surround it. And then we get these weird spots on the sun, which are called sunspots, which are actually areas where the sun's magnetic field kind of interacts with the convection on the planet, and it produces these darker and cooler spots. We say cooler, they're still hot, but they're cooler than the rest of the sun. So even the sun has its own complex structure that would take quite a while to go through if we wanted to look at it in great detail. After the sun, the next major feature of the solar system is going to be the planets. Now, each star can have its own group of planets. Again, we're focusing on our solar system. And once again, this is a diagram that is not at all drawn to scale. The planets like Earth is way too big compared to the Sun and to Jupiter. But again, it's just so we could fit it on the screen. And this includes Pluto, which is no longer considered a true planet. We'll talk more about that later. So in our solar system, there are 8 planets orbiting the sun. Pluto still orbits the sun. It's just no longer considered a planet. They all have a spherical shape. And like we said, many planets have been discovered outside of our solar systems orbiting other stars. And those would all be potential points for life and or of interest to exploration and study for us. Now, when we deal with the planets, and again, this is a diagram that's not to scale, the 8 planets are divided into 2 main groups. The first 4, Mercury, Venus, Earth, and Mars, are considered the terrestrial planets. The Latin word terra means Earth, and the terrestrial planets are all the Earth-like planets. It's actually where the term ET comes from. If something is extraterrestrial, that means it comes from outside of the Earth, and that's where that term came from, if you ever wondered that. So the first 4 planets are similar to Earth. We're going to take a closer look at them in a few minutes. And then the next 4 planets, starting with Jupiter, Saturn, Uranus, and Neptune, these are going to be known as the Jovian planets, because they're similar to Jupiter in that they are all large, they all have many moons, they're all gaseous, and they all have ring systems, even though you don't necessarily see them all. Saturn's the one that's most famous for it. If you look at Uranus, you can actually see some small rings around that in this diagram, which is nice to see. But they actually do have them. They're just a little bit harder to detect on the other planets. So when we look at this diagram, again, not drawn to scale, but what I do like about this is it shows the scale of the planets size-wise better than the other diagrams have. Of course, they're way too close together, but that's another story. So if you look at Mercury, Venus, Earth, and Mars compared to the Sun, you realize how small they actually are in comparison and how much larger Jupiter, Saturn, Uranus, and Neptune are. So when we group these out, those first 4 planets are known as the terrestrial planets. This is something you have to commit to memory because it'll be a major topic on our quiz that's coming up, and it's something that the Regents also likes if we ever get to that point. And then looking at the next 4 planets here, these are known as the Jovian planets. Think of that J, they're the ones that are like Jupiter, much, much larger and much more gaseous. So we're going to go through now and talk a little bit about the characteristics of the terrestrial planets first, and then the Jovian ones second. So the terrestrial planets are the ones that are Earth-like. They're the inner planets of Mercury, Venus, Earth, and Mars, which we have diagrammed out over here. They're mostly solid, so they have solid surfaces on them. You can walk around on them. And small diameters, and we can see that in the picture. Remember, diameter is the distance across a circle or sphere, which is what these planets are. They have a high density when you compare them to the other planets in our solar system. They have few or no moons. Earth has 1, Mars has 2, Mercury and Venus have none. They do not have ring systems, and they have rocky surfaces that are dotted with craters. Now, the craters are a little harder to find on the Earth because weathering and erosion has worn them away over time, but they are there. It's just a matter of weathering and erosion kind of hiding them. So let's take a look at each one of the terrestrial planets individually, and then we'll show you the Jovian planets. So the first planet we're going to deal with is the one that is closest to the sun, and that is Mercury. When you look at a picture of Mercury, a lot of people at first think it's a picture of the moon. They look very similar. You can see all the craters dotting the surface, and one thing that's really missing is you don't see that glow of an atmosphere around Mercury. And that's because it's so close to the sun that the sun has basically, destroyed and swept away most of the atmosphere of Mercury. There's a very small amount of gas surrounding it, but it's much, much thinner and hard to detect compared to, say, Earth's atmosphere. The distance, it's on average 57.9 million kilometers from the sun, so it's extremely far away, even though it's the closest one. It takes 88 days to make an orbit around the sun. So if you think about Earth, it takes a full year. It takes 88 days to go around the sun on Mercury, so it's much quicker. And it takes 59 days just to make one rotation on its axis. Remember, on Earth, that only takes 24 hours. So it would take 59 days to go through a cycle of day and night, while it would only take 88 days to go through summer, winter, fall, spring, which is very different. Eccentricity is something we're going to talk about later. The closer this number is to 0, the rounder the orbit will be. The higher the number it is, the highest it can ever get is 1, the more stretched out. So 0.206 is actually it's not a very round orbit. It's actually a little bit more oval shaped. We'll show you that in another lesson. Its equatorial diameter is small, 4,879 kilometers. Its mass, if you imagine the mass of Earth being set to 1, this is 6/100ths the mass of the Earth. So it is much, much less massive. Its density is 5.4 grams per centimeters cubed. It does not have a tilt on its axis. And look at the temperatures. There's a huge variation here, and that is because since Mercury does not have an atmosphere, it really doesn't retain heat well. The side facing the sun is very warm. 427 degrees is the maximum approximate temperature. And the side facing away is extremely cold, since the atmosphere can't hold on to any heat, at minus 173 degrees Celsius. So it's a pretty harsh, extreme environment. And the atmosphere, while minimal, is made of helium, sodium, and oxygen. And there are no known moons of Mercury. Venus, on the other hand, has an incredibly dense atmosphere, so much so you can't even see the surface of Venus. Its average distance from the sun is 108.2 million kilometers. It takes 224.7 days to make one revolution around the sun, so it's shorter than an Earth year, but it's definitely longer than Mercury. And this is one of the crazy things about Mercury. It takes 243 days to make one rotation on its axis. That means it actually takes longer to go through a cycle of day and night than it does to make a revolution and go through all the seasons. And that's a really strange thing. So a day is actually longer than a year, if you want to think in Earth terms, on Venus. Longer to go through a cycle of day and night than to go through all your seasons, which is really weird. Its eccentricity is very close to 0, so the orbit is very round. Its equatorial diameter is 12,104 kilometers, which is very close to Earth. It's very similar in size. So when you look at the mass, its mass is 0.82 that of the Earth. It's just a little bit less massive than us. Density is 5.2 grams per cubic centimeter on average. It has a lot of tilt. Its axis is tilted 177.3 degrees compared to what the Earth and the other planets. Its maximum and minimum surface temperature is about the same, 462 degrees Celsius, which is incredibly hot. Venus is the hottest of all of the planets. Even though it's the second farthest from the sun, you would think Mercury would be. But the difference is Venus has this insanely dense atmosphere, which is mostly carbon dioxide and nitrogen. We know carbon dioxide is a greenhouse gas, so Venus is very efficient at trapping heat in its atmosphere, and that's why it is the warmest of the planets. And there are no moons of Venus. Then we get to Earth, one that you're familiar with. I love the satellite pictures of Earth. It's a beautiful planet to look at, and when you look at it, what really stands out is the water. We have the only planet in our solar system with vast, which means lots of liquid water on the surface. So that's what's really unique to Earth in our solar system. So the Earth has an average distance of 149.6 million kilometers from the sun. It takes us 365.26 days to make one revolution, or 1 year. Remember that 0.26 is the reason why we have leap year every 4 years to adjust for that. The period of rotation at the equator is 23 hours, 56 minutes, and 4 seconds. And I'm sure someone's like, wait, I thought it was 24 hours. Well, if you add into the fact that we're also revolving around the sun, it does work out to be 24 hours for a period of day and night. But in this case, the specific rotation is a tiny little bit shorter than that. That's not a detail you need to worry too crazily about. The eccentricity, 0.017, is very close to 0. So we have a very round, it's not perfectly round, but it's a very round orbit. And similar to Jupiter in size, we're at 12,756 kilometers in diameter. Since we're comparing to Earth, we have the same mass because we are the Earth. The density, 5.5 grams per centimeters cubed, is actually the highest of all the planets. And our tilt on our axis is 23.4 degrees. A lot of times we tell you 23.5. The decimal continues out a little bit, but it actually rounds down to 23.4. And the max and min temperature, our maximum recorded temperature is 58 degrees Celsius, and the coldest is minus 88 degrees Celsius. We know our atmosphere is mostly nitrogen and oxygen, and we have one moon, which is the moon. This is actually kind of a cool picture. This is it's a little grainy because it's an old picture and the resolution wasn't that good. But this is a picture taken by the Apollo astronauts as they were orbiting the moon of the Earth in the distance. So you know how we have sunrise and sunset and moonrise and moonset? Maybe you would call this an Earthrise or an Earthset, depending on which way it's going. But it's kind of a different perspective to see the Earth at. Then we get to Mars, planet that we have a lot of interest in because we'd like to think that maybe one day, and hopefully we will, that we would actually be able to actually get people on Mars and see what it's like and maybe even be able to live there at some point in the future. So when we look at Mars, one of the things it's known as is the red planet. It has to do with a lot of this oxidized iron on its surface. And when we look at the distance from the sun, it's much farther than the Earth, 227.9 million kilometers. It takes 687 days to make an orbit around the sun, so it's much, much longer compared to Earth's 365 days. It's almost twice the amount. It's not quite there, but it's almost, if you want to think rough terms. It takes at the equator, it takes 24 hours, 37 minutes, and 23 seconds to make one rotation. So the periods of day and night on Mars are longer than they are on Earth by a little bit. It has a slightly more eccentric orbit, which means it's not as round as the Earth's. It's smaller than the Earth. Its diameter is about roughly half the size, 6,794 kilometers. Because it's smaller, it's much less massive. It's 11/100th the mass of the Earth. Its density is a little lower too, 3.9 grams per cubic centimeter. Has a tilt of 25.2 degrees, similar to the Earth. And its maximum temperature, 20 degrees Celsius. That's 68 Fahrenheit. So that is a survivable temperature for humans. Of course, on the flip side, it can get very cold. Minus 153 degrees Celsius is really chilly, and that's even colder than things we've recorded in Antarctica. But it's a reasonable temperature range that humans could survive, but especially on that warmer end. And its atmosphere, carbon dioxide, nitrogen, and argon. Notice oxygen is missing. That is something we'll have to figure out if we ever want to go to Mars. We have to have a way to get oxygen, obviously, so we can live. And it has two moons called Phobos and Deimos, which we'll see a little bit later. So those 4 planets are our terrestrial planets. Now we can kind of go ahead in just a second and take a look at our Jovian planets. But before we do that, we've got one picture from Mars. One of the cool things about Mars is we have our rovers roaming around the planet so you can take a look at the surface. And this is one of the pictures that we got back from Mars. This rock is very, very interesting to geologists and astronomers alike because it is sedimentary in nature. And we know sedimentary rock forms in water environments. So at some point in time, there must have been water on the surface of Mars. And we would love to know, where did it go? Is it still there? Is it combined in other chemicals now? Is it part of the rock? Where did it go? And that's a big question we're trying to figure out on Mars. Now let's switch gears and take a look at the Jovian planets. Remember, J for Jupiter. They're similar to Jupiter in that they're Jupiter, Saturn, Uranus, and Neptune. And these are large gaseous planets, so they're all gas. They have very large diameters, meaning they're very big. And they have low densities, especially when you compare them to the other planets. And that's because they're gas. There are no solid surfaces that we know of, and they have many moons, lots of moons, and they all have ring systems. Even though Saturn's the one that's really the one that's easy to see, the others do have them. They're just smaller and harder to see, a little bit fainter type of ring system there. So let's take a look at these guys one by one. When we start off with Jupiter, there are these kind of belts or bands. Almost reminds me of the prevailing wind diagram where we separate things out by latitude. We also notice one of the most famous features of Jupiter is the red spot, which is a giant swirl in its atmosphere, we'll call it. And this has been observable on Jupiter for as long as astronomers have been recording it. Many people liken it to sort of like a storm, a low-pressure system on Earth, but it's some kind of swirling eddy on the planet, and it's a very neat feature. We're also seeing a solar eclipse in this example. What we actually have is one of the moons of Jupiter has gotten between the sun and Jupiter, and the moon is casting a shadow on Jupiter, which is kind of neat. I don't know which moon it was. Jupiter has a lot of moons, which we'll show you. So distance-wise, 778.4 million kilometers from the sun, really far. Takes 11.9 years to make one orbit around the sun. So if you think about it, I mean, you guys are 13, 14, 15 years old. So in your lifetime, Jupiter's only went around the sun completely once, which is kind of a crazy thing to think about. It rotates very quickly, 9 hours, 50 minutes, and 30 seconds at the equator. Its eccentricity is 0.048, so it's pretty close to being a round orbit, just a little bit off. Very large. Jupiter is the largest planet, that's worth knowing. 142,984 kilometers at the equator for its diameter. It's 317.83 times the mass of the Earth, so much more massive. But its density is much less, 1.3 grams per centimeters cubed. Again, it is a gas. It has a small tilt, 3.1 degrees. We don't have maximum surface temperature data available because we really don't have a surface to measure off of on Jupiter. So that's not going to be available for the Jovian planets. And its atmosphere, similar composition to the Sun, hydrogen and helium. And there are 67 known moons around Jupiter, and I feel like that's a number that every time I look at, we seem to have to update. We find new things all the time. Then we get to Saturn. Of course, Saturn is most famous for its ring system, which is basically lots of dust that's in orbit, maybe some ice, like methane ice and things like that, trapped in orbit around it. We're seeing some solar eclipses, those little black dots on Saturn from these moons that are sitting here, actually the ones that are casting the shadow. So you can see a few of the moons in this image here. And Saturn's very far from the Sun, 1,426.7 million kilometers. It takes 29.5 years to make one orbit around the Sun. So when you guys reach 29 and a half years old, Saturn will have gone around the Sun just once. That's how long it takes. Its period of revolution, 10 hours and 14 minutes. Rotation, that is. So it spins very, very quickly. Its eccentricity, 0.054, so it's definitely not a perfect circular orbit, but it's not too far off. It's the second largest planet, 120,536 kilometers for its diameter. It's 95.16 times the mass of Earth. It has an extremely low density. It's the least dense of all the planets at 0.7 grams per centimeters cubed. Weird thing about that, if you think of the density of water, it's 1.0. If you took a sample of Saturn, it would actually float in water, just to give you an idea of how low the density is. It has a tilt of 26.7 degrees. And just like the other Jupiter, the Jovian planets do not have temperatures available because we don't know what the surface is. We've never detected one. And just like Jupiter and like the Sun, its atmosphere is mostly hydrogen and helium. 62 known moons orbiting Saturn. Then we get to Uranus, and a lot of astronomers will pronounce it Uranus so that we can avoid all the Uranus jokes, but if we were in class, we would be calling it Uranus and making all sorts of funny jokes about that. One of the ones that I always like to make is that there's a town in Connecticut called Mayanus, which means if you had a telescope and you brought it there, you could view Uranus from Mayanus, which is just a really weird sentence if you think about it that way. And if we ever do make it back to school, just remind me, there are Uranus jokes that we can go with all day. And if you ever have a good one on your own, if you feel like emailing it to me, as long as it's appropriate, I would be very entertained to hear any of your Uranus jokes. So moving into Uranus here, that sounds weird too. I didn't even mean that. So looking at Uranus, that's weird too. No matter how you phrase it, you're going to have some interesting comments to go with here. But basically, Uranus is this bluish looking planet. It is 2,871.0 million kilometers from the Sun, and it takes 84 years to make one revolution. So when you turn 84 years old on your 84th birthday, remind yourself that Uranus has only made one orbit around the Sun at that point in time. Now, if you divide 84 by 4, you get 21. That means the seasons, if you want to think of it this way, on Uranus last 21 years. So you'd have 21 years of summer, 21 years of fall, 21 years of winter, and 21 years of spring, if you think about it that way. Kind of a strange thing. Rotates pretty quick compared to the Earth. At the equator, it rotates 17 hours and 14 minutes. Eccentricity, 0.047. I know that number doesn't mean a lot yet, but we're going to focus on it in the future. So it's a relatively round orbit. It's not as big as Saturn and as big as Jupiter. Of course, Jupiter's the biggest, but it's still big, 51,111 kilometers. It's 14.54 times the mass of the Earth. Its density still low, like all the Jovian planets, 1.3 grams per centimeter cubed. Axial tilt is pretty extreme, 97.8 degrees. Surface temperature is not available. And its atmosphere, hydrogen, helium, and methane. That's another gas we're adding into the atmosphere of Uranus here. And it has 27 known moons. Then we get to Neptune, another bluish looking planet, similar atmosphere to Uranus. Much, much farther though, 4,498.3 million kilometers from the Sun. It takes 164.8 years to make one orbit around the Sun. So there's not a perfect person alive on the Earth that has ever been alive long enough to have Neptune make one orbit in their lifetime. Gives you an idea how long it is. Rotates quickly, 16 hours. Its eccentricity is very low, 0.007, which means it has a very round orbit because it's very close to zero. Very similar in size to Uranus, it's just slightly smaller, 49,528 kilometers. Its mass is 17.15 times that of the Earth, density 1.8 grams per cubic centimeter, axial tilt 28.3 degrees, no temperature data available, same atmosphere composition as Uranus, hydrogen, helium, and methane, and it has 14 known moons. So now we have to say to ourselves, well, what about Pluto? It used to be a planet, and now it's not. So here's the explanation. In 2006, a new and distinct class of celestial objects was named by the International Astronomical Union, the IAU. They were called dwarf planets, and Pluto is considered to be one of these dwarf planets. According to the IAU, a celestial body is classified as a dwarf planet if it exhibits the following characteristics. It's in orbit around the Sun, which Pluto is. It has sufficient mass for its self-gravity to overcome rigid body forces, so that it assumes a hydrostatic equilibrium or nearly round shape, and Pluto does have a nearly round shape. It has not cleared the neighborhood around its orbit, meaning that there are other objects nearby and that the planet's gravity has not cleared those out over time, or the dwarf planet, I should say. And it is not a satellite or a moon of another object. So what really makes Pluto not considered to be necessarily a planet is this one right here, that it has not cleared the neighborhood around its orbit. Pluto's orbit is also very eccentric, meaning it's more stretched out, and it actually gets closer to the Sun than Neptune every once in a while. And that's another factor that makes it a little bit odd as a traditional planet. So what about Pluto? Whether you want to consider a planet or a dwarf planet, it doesn't matter. It's still orbiting the Sun. It's still there. Here's an awesome picture of it. We finally got some high resolution pictures from one of the spacecrafts that finally made it out there. It takes a long time to send a space probe out this way. We're talking decades to get something out that far. And it is 5,906 million kilometers from the Sun. It takes 247.9 years to make one revolution, which is really crazy. If you think about the fact that the United States began in 1776, as long as we've been a country, Pluto has not made one revolution around the Sun, which is pretty wild. Its period of rotation is slow, 6.4 days to make one rotation compared to the Earth, and its eccentricity is much higher than we've seen with other objects, 0.249, so it's not that round of an orbit. It's also small, 2,368 kilometers its diameter. It is much less massive than the Earth, 0.00218 times the mass of the Earth. Its density is very low, 1.9 grams per centimeters cubed, has a lot of tilt, 119.6 degrees, and it's very cold. Max temperature minus 218 Celsius, min minus 240 degrees Celsius. That's partly because it's so far away from the Sun, and I believe it also has a very thin atmosphere too. Its atmosphere is mainly nitrogen, methane, and carbon monoxide. Not dioxide, but carbon monoxide. And there are 5 known moons of Pluto. Some astronomers kind of theorize that Pluto may have been an asteroid from the Kuiper Belt that was kind of trapped nicely in the Sun's gravitational pull, and that's another theory and idea out there on Pluto. Now, Pluto is not the only other dwarf planet. There are currently 5 officially classified dwarf planets in our solar system. One is called Ceres. Then we have, of course, Pluto. We have Haumea. And this one, it looks like Makemake, but you pronounce it Makemake. And then we have Eris. Now, Ceres, down over here, it's a very pixely picture. It's not very well focused because it's a small object. Ceres is actually in the asteroid belt between Mars and Jupiter. So it's part of that asteroid belt. Then we have Haumea, Eris, and Makemake. The images are very grainy because these objects are so far away, but these are out toward the Kuiper Belt, out where we would basically find Pluto, out in that part of space. Now, another 6 objects are almost certainly dwarf planets that have been discovered, and they're waiting for their official classification. And there may be as many as 10,000 dwarf planets out there, and perhaps even more, all waiting to be classified. Then we get to asteroids. Asteroids are either rocky or metallic objects that orbit the Sun. When we say rocky, they're silica-based, similar to igneous rock on the Earth, and metallic, they contain a lot of iron and nickel, much like the core of the Earth. And these would be left over, basically, from the formation of our solar system. And the vast majority of these asteroids are in a belt between Mars and Jupiter. Kind of interesting that it separates the terrestrial planets from the Jovian planets, and maybe that's not a coincidence. So the Earth-like planets and the gaseous planets are separated by the asteroid belt. It's a good way to kind of remember where it is. Now, if we look at this diagram that we open with, We have our 4 terrestrial planets, Mercury, Venus, Earth, and Mars. Then you have the asteroid belt. You'll notice Ceres is actually that dwarf planet, the first one listed up there. And then we have Jupiter, Saturn, Uranus, Neptune, the gas planets. And then we actually get to the Kuiper belt, which is basically another asteroid belt, but farther out. So the main asteroid belt between Mars and Jupiter, and then there's this secondary one a little bit farther out. And then moons. Where do moons fit into this whole thing? A moon is a celestial body, meaning it's out there in space, that orbits a planet. So to be a moon, it has to be in orbit around a planet. And some planets have few moons, some have none, and others have many. The one on the left that you're seeing in the picture, this is Earth's moon, which you guys are all familiar with. And then the 2 next to it are Phobos and Deimos, which are the 2 moons of Mars. You'll notice that these 2 moons are not nearly as spherical as the Earth's moon, which is kind of interesting. Maybe they almost look to me like asteroids, and perhaps they are asteroids that were captured in the Mars gravitational pull. I'm not sure if that's true or not, but just something that, for me, it looks like it would make a lot of sense. And then looking at their surface, they're all dotted with craters. They have no atmospheres to basically wear them off. So when things do collide with them and they leave a crater, it stays there for quite some time. And then we get to comets. One of the most fascinating objects that are out there in the solar system. They're these neat objects that are actually really dark when they're out there in space. They only start to get this bright glow to them when they get energized as they get closer to the sun. And the sun vaporizes the ice that makes them up. It's water and methane ice. And it produces this beautiful tail that gets illuminated as well as you get closer to the sun. So comets are a topic that we're going to talk more about in the future. We're going to have a separate lesson on those once we get a few more topics done. So we'll get into this in a lot more detail, but comets are really, really neat objects out there. They are orbiting the sun, which is why they're a part of our solar system, and we'll get into more details on them in the future. The last thing we're going to talk about with our solar system are meteoroids, meteors, and meteorites. And they all have different names, but it really just depends on where they're located. They're kind of the same idea. So meteoroids, I should say, are very small, solid fragments that orbit the sun. Most of them are tiny, the size of a dime or a sand grain, so they're small little particles. And then as they enter the Earth's atmosphere, they're going incredibly fast, and then all of a sudden they hit our atmosphere, which is the first time they're colliding with molecules that are densely packed together, and it heats them up due to the force of friction. So this causes them to basically start to glow and vaporize as they go across the sky, and these are what most people think of as shooting stars. They're not really stars, they're actually pieces of debris entering our atmosphere and burning up from all that heat they're generating through friction before they hit the ground. So when they're in space, we call them a meteoroid. When they enter our atmosphere, they're known as a meteor, and our atmosphere protects us. Most of these things basically burn up before they hit the ground. But if they do make it to the ground and we actually have it on the surface of the Earth, then it's called a meteorite. So that's really the difference between the 3 terms. And it's a good thing we have a nice atmosphere like this, because otherwise we'd be hit by meteors all the time. On average, once every 10 minutes, one of these things enters the atmosphere above us and burns up before it hits the surface. If it didn't, we'd have objects, people, and everything constantly getting hit by these meteors, and we'd have a lot more craters on the surface of the Earth. So we're thankful for our atmosphere for protecting us. And this is what one actually looks like when it's entering into the atmosphere. This is a picture of a meteor shooting across the sky. So this was a meteorite in space, a meteor entering our atmosphere, and more than likely it burned up and did not make it to the surface. If it did, it would become a meteor. And there's actually a smaller one streak forming here, so there's another one entering the atmosphere above it. And the color that they streak across the sky has a lot to do with the composition of the different metals that are in there, different materials will burn up and give you a slightly different streak going across the sky. They're really impressive to see, and they happen very, very fast. These are quick-moving objects across the sky. If you blink, you can miss it, kind of a thing. And then all the data we've been talking about with these planets, it's not something you have to memorize. A lot of that important data is sitting here in the reference tables on page 15, and our next topic here is going to be to take some time and go through this particular diagram.